Assalamu alaikum. In this lecture, we will discuss some examples. I will start with the first one. And let's assume we have the following open loop block diagram consists of a digital filter D of Z. After that, we have the zero order hold. The transfer function of the zero order hold is 1 minus exponential of minus TS over S. And after that, we have a plant. The transfer function for the plant is 1 over S plus 1. And let's assume the output here to be C of S. And the input, let's call it E of S. This will be E of Z. Let's call the output of the digital filter M of Z. And the output of the zero order hold will be the reconstructed of the M of S bar, and the output as we called C of S. In time and discrete domain, this will be E of T, this will be E of K T, this will be M of K T, this will be M of T bar, and this will be C of T. As we said, this is a digital filter. And this is the zero order hold, and this one is the plant, let's call it GP of S. Now this is a sampler, and if you recall, this is a representation for the analog to digital converter. And here we can assume that the sampling period is T. Now this is the zero order hold, and as we said before, is a representation for the digital to analog converter. So we can replot it in terms of the analog to digital converter and the digital to analog converter. As first thing here we have analog to digital converter. After that we have the digital filter. Cascaded with the DAC or the digital to analog converter. And after that we have the plant, which is the GP of S. The input is E of S, and the output here we assume is C of S. Now we need to determine the unit step response if the digital filter is described by the following difference equation. Is described by the following difference equation. M of KT is given as 2E of KT minus E of k minus 1 t. Now the first thing, if we need to find the unit step response, this means that the input is unit step. Which in term of Laplace, E of s is equal 1 over s. Now, E of z is the unit step sequence, which is the z transform of E of s, and we know that the unit step sequence is given as z over z minus 1, and this is the unit step sequence. So now, from our understanding of the block diagram, so from the block diagram, we can call the plant with the zero order hold G of S. So from the block diagram, we can write C of Z equal to D of Z, G of Z, E of Z. Now, G of Z will equal the Z transform of the zero order hold, which is 1 minus exponential minus Ts over S, multiplied by the plant, which is 1 over S plus 1. Now this will equal to 1 minus Z minus 1, the Z transform for 1 over S plus 1. Now, this one we can solve it using the residual method. So, here we have two simple poles. So, the poles are S equal to 0 and S equal to minus 1. So now, the Z transform for 1 over S plus 1 will equal to R1 of Z at S equal to 0 plus R2 of Z at S equal to minus 1. So R1 of Z will equal the limit when S go to the root, which is the 0. I will multiply the root by the function itself, 1 over S plus 1, Z over Z minus exponential of Ts, and if I evaluate, this will equal Z over Z minus 1. So the second residue R2 of Z evaluated at the root S minus 1 will equal the limit when S go to minus 1, S plus 1 multiplied by the function 1 over S plus 1, Z over Z minus exponential of Ts. And this will equal, if we evaluate, this will equal minus Z over Z minus exponential of minus T. So now R1 plus R2 will equal to Z over Z minus 1 minus Z over Z minus exponential minus T, which will equal to Z minus exponential minus T minus Z minus 1 over Z minus 1 multiplied by Z minus exponential minus T. So we need to find G of Z. Now G of Z was equal 1 minus Z minus 1 of the Z transform of 1 over S plus 1. Now the Z transform, this one, we already find it here. So simply this means that G of Z will equal, we can write 1 minus Z minus 1 as Z minus 1 over Z. And this one here, we already found it. So it will be multiplied by 1 minus exponential minus T Z over Z minus 1 Z minus exponential minus T. So if we simplify, this will equal to 1 minus exponential minus T over Z minus exponential minus T. Now d of Z is given by a discrete equation. So from here, this will be M of Z will equal 2E of Z minus Z minus 1 E of Z. So now D of Z, the pulse transfer function for the digital filter, the input is the E and the output is the M. So M of Z over E of Z, and this will equal to 2 minus Z minus 1, which can be written as 2Z minus 1 over Z. So now we have the digital filter, and we have the G of Z. So C of Z will equal D of Z, G of Z, E of Z. So C of Z can be written as D of Z is 2Z minus 1 over Z. G of Z is equal 1 minus exponential minus T over Z minus exponential minus T. And E of Z is the unit step sequence, so Z over Z minus 1. And we will end up with 2Z minus 1 over Z minus 1 multiplied by 1 minus exponential minus T over Z minus exponential minus T. Now simply, if we need to find C of KT, in this case we need to find the Z inverse of C of Z, and let's assume we'll use for that the partial fraction expansion. But remember, we will not do the partial fraction expansion for C of Z, we'll do it for C of Z over Z, because all the Z transform has a Z in numerator in order to match the factorized terms with the terms in the table. C of z over z by using the partial fraction expansion will equal to 1 minus exponential of t over z plus 1 over z minus 1 plus exponential of t minus 2 over z minus exponential of minus t. Now we can calculate c of z, which will equal to 1 minus exponential of t plus z over z minus 1 plus z exponential of t minus 2 over z minus exponential of minus t. Now we can find c of kt. Now the first one here is the impulse, so 1 minus exponential of t multiplied by delta of kt plus the second term here is the unit step sequence, so 1 plus now the term here is exponential of t minus 2 multiplied by exponential of minus kt, exponential term, constant multiplied by exponential term. Now, if we need to simplify it, c of 0 will equal 1 minus exponential of t plus 1 plus exponential of t minus 2, and this will equal to 0. So simply now we can write c of kt will equal to 1 plus exponential of t minus 2 e to the power minus kt, where k is equal to 1, 2, 3, and so on. Another example. To evaluate another advantage for the zero order hold. Now let's assume that we have a simple block diagram consists of one block where the input is e of s and the output is y of s, and let's assume it's 1 over s plus 1, and we need to find the y steady state due to unit step input. So simply we know that for unit step input y of s will equal 1 over s plus 1 multiply 1 over s, which is the unit step. So y the state in time domain will equal the limit when t go to infinity of y of t, which will equal the limit when s go to 0 s y of s, and this, if we evaluate, it will equal to 1. Now assume a sampler has been introduced. So simply the same block diagram, instead that we are introducing a sampler without zero order hold. So this is e of s, this will be the e start of s or e of z, and this will be the y of s, 1 over s plus 1. Now from the block diagram, we can say that y of s will equal 1 over s plus 1 e start of s or if this one is g of s, then y of s will equal g of s e start of s. If you start the both side, so this will be y start of s will equal g start of s e of s, which can be written as y of z is equal to g of z e of z. So now we can evaluate y of z to be equal. Now this one we already have it. This one is the z over z minus exponential of minus t, and the unit step sequence is z over z minus 1. Now we need to evaluate the y steady state, which will equal the limit when z go to 1 minus z minus 1 y of z. So y steady state can be written as the limit when z go to 1, z minus 1 over z multiplied by y of z, which is z over z minus exponential of minus t, z over z minus 1. So this one will be cancelled, and we'll end up with z over z minus exponential of minus t evaluated at z equal to minus 1, which will equal 1 over 1 minus exponential minus t. So if we assume that t is equal 1 second, this means that y steady state will equal 1.58, which is not identical to the continuous time system. In the continuous time system, y steady state was equal to 1. Here, the steady state will depend on the sampling time. So now, what about if we introduce a zero order hold after the sampler? What will happen? So now let's assume that we are introducing a zero order hold. And here we have the plant, which is the P of S, which is 1 over S plus 1. And here the output is Y of S. The input is E of S. The sampling period is T. And this will be now E reconstructed of S. And this will be the E start of S. Now again, y of s will equal to 1 minus exponential minus ts over s, which is the zero order hold transfer function, multiplied by gb of s, which is 1 over s plus 1, multiplied by e start of s. So from here, y of z will equal g of z e of z, and g of z will be the z transform for the zero order hold 1 minus exponential minus t s over s, 1 over s plus 1, and the plant, so this will be 1 minus z minus 1 the Z transform for 1 over S plus 1. And we already calculate this one in the previous example. So now we can write y of Z equal to Z minus 1 over Z multiplied by Z over Z minus 1 minus Z over Z minus exponential minus T multiplied by the unit step sequence, which is the Z over Z minus 1. Now this will cancel this one, this will cancel this one, and we will end up with Z minus exponential minus T over Z minus 1, Z minus exponential minus T. Now, if we need to evaluate y steady state, which will equal the limit when Z go to 1, 1 minus Z minus 1, y of Z, it will equal to 1. So now we have the same steady state value in the continuous time domain and the discrete time domain with the help of using a zero order hold, and this is also another advantage of using the zero order hold.